All right. Welcome, everyone. So tonight we're going to talk about distributions. So probability, that's good that was there. But let me get to this slide because there are a couple of announcements. Jumping to the third one, for those who did not stick around last week to solve the question of how do you solve that card game through a simulation, the R script to do it is here. I think even Angela and I stayed on a little bit and I reworked the function to be a little bit more efficient. For those wondering what the issue was, is I was returning 20 and not 10. I mistyped from the slide and that's what it was. So kind of a silly, embarrassing mistake, but we all make them. The big announcement next week, and we should probably, Angela, probably send an announcement on Blackboard maybe on Monday or something. We have to do next week's meetup early at 3 p.m. I know that's probably inconvenient for most of you if you're working. So if you can't attend, we completely understand, but do watch the recording. You can watch. I'll make sure to have it up so it's up by 8 o'clock if you want to keep your regular scheduled time and watch it at that time. We have some colleagues coming in from out of town, and we have a big thing going on the project, our DAX project, on Thursday. So we're going to do some preparation on Wednesday night. So I'm sorry about that. So we'll send another reminder. So next week, 3 p.m. if you want to come live. Otherwise, the recording will be up. To counteract that bad news, maybe some good news is we're going to push the midterm back 1 week. So I think it was originally scheduled to open on the 9th. It's not going to be open till the 16th. I think I was just trying while we were getting ready here. I don't know if it kind of updated on the website yet. Hey, it did. Look at that. So it'll become available on the 16th and will be due on the 22nd. So we want to include chapter 5 in that. So you'll have basically the first 5 chapters covered in the midterm. Which, even though it's not half the book, it's probably about half the content, because I think the second half is more dense. And then just a last reminder, I'm giving a talk Tuesday night on our package development. If this is something of interest, you can sign up on this meetup page. It will be recorded, and I'll post the recording on the course website. But it's you're not going to be tested or anything. It's completely optional. All right. Any questions about that stuff?
Are the non-graded homework sufficient to do the midterms?
Yes. Yeah, that's kind of, if you read through them and you think I kind of know this, then you're good. It is going to be multiple choice though, so not open-ended where the homeworks are. But in terms of content, I think that would be that's going to be sufficient. And the labs too. We might put a short answer, but it's going to be mostly multiple choice. And it is open book. You can use your notes and the textbook and what have you. Just don't collaborate.
Okay.
What's that?
I have a quick question.
Yeah.
So for the exam, is that like we take it at like a certain time, or is it like open for a limited amount of time?
It's going to be open for the week. Yeah, I'm not. Actually, Angela probably knows this better. Am I right to kind of hate timed assessments? It's sort of been my belief, but I'm a little out of date of that literature.
I am, but I mean,
you're not in favor of time.
I'm not in favor of time assessments. No. I think having a week to take this assessment, just knowing what it is more than enough time, right? So I think the reason we give that, like the time for you, is for you to choose a day that actually works for you to, I would suggest to just sit down and complete the assessment. I think you can do that. Yeah. But for us to have it open for the span of 1 week is not for you to say, oh, I'm going to answer one question today and then another question tomorrow. Then that sort of, I don't know, that stretches out the exam too much. But
don't recommend it.
Yeah.
We're also not putting restrictions. I think you can in Blackboard say, well, once you start, you have a fixed amount of time, but
yeah.
we didn't set it up that way. So, but
Yeah.
we'll probably look at the timestamps, and this is the first semester we're taking this approach. So we'll see how it goes. Does that help answer your question? What I often recommend is look at it on the 16th, and then, hopefully at that point you have a good sense of where you are and go, oh, this will be, I can get through this.
Yeah.
Or, oh boy, I got to brush up. You got a week to brush up. So it is a summative assessment, but I also think Angela would agree you should learn from it. It's another
Yep.
learning opportunity.
Is there a detail for the midterm, like which chapters to read, like
One- 1 through 5.
What is 1 through 5?
Yep.
Okay. Thank you.
So we're covering chapter 4 tonight, right?
Yep. Chapter 5 is 2 weeks long.
Yeah, we'll take 2 weeks. All right.
Jason,
Oh, yeah.
Jason, one
Go
quick
ahead.
question about the final project. Is it too early to start that, or should we have more of the class under our belt? Like when's a good shotgun in the air moment
Good.
for that?
Good question. So I'll just say, if you looked at the page, you're going to be asked to analyze a data set using one of the statistical methods you're going to learn this class with a data set of your choice. And there's some, options there. So I don't think it's too early if you come across a data set that oh, this looks interesting. And it's something you could either do test whether there's a difference between some groups, or if you want to run some kind of regression where you're going to try to predict some outcome from some other variables. So if you see that, kind of, grab it. I think, if you're not reading 538, although admittedly, I have muted Nate Silver for a while. I need to take a break from him, but 538 publishes all their data sets. So if you read that, and they do a lot of fun articles, and there's a 538R package. A lot of students like to use that. So, or if you hang around Kaggle and you see they, or even past competitions, they have data sets you could use, or, so it's not too early to think about that, but I think we'll introduce it probably right around the midterm is available,
Yeah.
because you'll have enough background.
Yeah. You can also start, I think you have enough knowledge now to explore variables descriptively. So doing, summary statistics, plotting graphs to see how the distributions look, things like that. So just to see variables and what might interest you in terms of a research question.
Thank you. That answers my question.
Yeah, and we have I have a slide, and I don't know where it shows up, that will go into some more details on this. We could push it up to next week or the week after, if you're chomping at the bit to get started. All right, cool. All right. So we talked a little bit about distributions last week, actually, no, we talked about probability models, right? And so we're going to kind of extend that a little bit and kind of try to define this notion of a distribution, because that's kind of going to be the crux of how we're going to do a lot of statistical tests the remainder of the semester, and there's going to be a certain pattern that we'll start to extract, and I'll try to summarize it next week. But for now, let's, this is that coin toss example that we talked about last week, where I'm just going to flip a coin 100 times. If I get heads, I'm going to add 1. If I get tails, I'm going to subtract 1. And, I'm going to look at the trajectory over time. And here looks like at the end of 100 runs, I ended up with 4. So I got 4 more heads than tails, right? So what we want to do here is say, well, let's define our event essentially as flipping a coin 100 times. Right. Kind of alluded this to last week. It's like, well, 4 is not 0. We would expect in a fair coin to get the same number of heads or tails, but probably intuitively we think, well, 4 one way or another is probably not too bad. So what we want to start to look at is that variation or that deviance away from the expected value. So in this case, our expected value is 0. And so here on this particular run, we ended up with 4. What happens if we do this experiment of flipping a coin 100 times, lots and lots of times, to see where we end up at the end, right? So that's what we're doing on this slide. So here, in fact, we're going to do it 1,000 times. So I'm creating this vector called samples. I'm initializing it with NA, which is the missing value indicator in R, 1,000 times. So I'm going to loop through each one. This code here is precisely the same code here. But so I get that vector of coins, actually this whole line. But what I'm doing is at position I, right, because I is going to be set to 1, then 2, all the way to 1,000, is just taking, so I'm doing that cumulative sum. So, and I'm taking the last value from my coins vector and saving that, right? And so I have now this vector of samples, which is 1,000, and here I'm showing the first 15. So what is this vector? This is the end value after flipping a coin 100 times. So in fact, I flipped a coin, what would that be? So I have to add 200,000 times, 1,000 times 100. Okay, so you can see on the first one, I got -8, 6, -14, et cetera, et cetera, et cetera. So let's look at this. Let's actually plot this vector. And this is what we get, right? And probably not anything, new, right? This looks like a normal distribution that I'm sure everybody's kind of heard about and have talked about, but but just take a moment and realize what we did. We just simulated flipping a coin and taking that endpoint and, plotting that. And that follows this kind of distribution. So it's centered on 0, right? And it kind of flares out. So the further away we get from 0, the fewer occurrences of that outcome we had. So we actually had one instance in that 1,000 that was, close to -40, right? So, and then the highest we got was 30. So this is bounded. And if you remember, what is the range of possible values? If we're flipping a coin 100 times, we could get all heads and be at +100 and all tails and be at -100. But our actual observed values are kind of constrained here, kind of clustered to that center. Okay. So this is in fact called a distribution. In this case, it's a distribution for a quantitative variable. And specifically, we're going to see that this particular distribution follows the normal distribution. And we'll define what normal means in a moment, right? So when we talk about distributions, there are going to be kind of 2 key properties we're going to be interested in. One is the mean or the center, or some kind of center, but typically we're going to use the mean to represent that. So in this case, we could see the mean here is 0.066, right? So after 1,000 runs, we're pretty close to 0, not exactly. And we have a standard deviation. So remember, that's the square root of the variance. And we did that variance app, right? So we looked at variance in terms of deviation away from the mean as square deviances and the sum of that, and you average it, right? So if you don't remember that, go back and look at that app to try to familiarize us. We're going to just take the square root of that. So that gives us, in this case, it's pretty close to 10, where I'm just going to round this to 10 as we go through, but we got 9.989 technically. So that's just from this run. If I rebuild the slide deck, I'm going to get a slightly different number. Okay, so let's look at some interesting additional properties and this is what we're going to leverage as we go forward. So if we want to look at the number of samples or the number of outcomes that fall within one standard deviation. So here, this is what I'm doing using the old school R subsetting. So I'm taking, if the samples is greater than or equal to the mean minus the standard deviation, and it's less than or equal to the mean plus the standard deviation. So what this is going to do is subset the samples that only fall within one standard deviation. So if I take the length of that divided by the total length, so for this particular example, this is always 1,000, and this is going to be something smaller than 1,000, we end up with 68.6%. So in other words, 68% of our coin experiments fell within one standard deviation of the mean. So here I'm going to do 2 standard deviations. So the only difference here is I'm adding this multiple, right? And I get 95% of the experiments fall within 2 standard deviations. And now we go 3, right? And we get 99.8. So this is all derived from this little example of just flipping a coin 100 times repeatedly, right? And so if we go to the formulation for the standard normal distribution, sometimes called the Gaussian curve, right? This is what it looks like. So we have f of x given some mean and standard deviation, and we'll look at mean and standard deviation. So in this case, our mean is, what was it, 0.066, and our standard deviation was roughly 10, right? This is what it is. So you can see where the mean and the standard deviations here. E is the natural logarithm, if you don't remember. So sigma here is also the standard deviation, and we have the square root of 2 pi. If I just plot this, so if we look at this little function here, I'm using base R. So I'm just going to go from -4 to 4 and have 200 elements. And then I'll introduce more formally these different functions, but the d norm function is really just going to give me the height of the normal distribution at a particular x value. So I'm going to pass in x, and I have to define a mean and standard deviation. And so I plot it. So this is what it looks like. If I go, 1 standard deviation from this formula above and below, I get 68%. So just a quick digression. So if you've took calculus 2, right? Well, first of all, I should say a key property of this distribution is that the area under this curve is 1. And that's really important. And we're going to exploit that a lot. So now we can interpret these areas as probabilities. Okay. So if I take the integral, right, from Calc 2, from -infinity to infinity is equal to 1 of this function. Now, if I take the integral from -1 to 1, right, I'm going to have that closed form, I get about 0.68. And if I go 2, I get roughly 95%. And if I go 3, I get 99.7. So this phenomenon happens a lot in nature, right? And this becomes really important for us to leverage to make inferences, right? So realize this was just from this simple simulation. We were able to get 98, 95, and 99.8, which correspond to the properties of this normal distribution. Okay. So why is this important? Well, we can do some really interesting things. So we could see if we go back to our original coin toss, right? It's not linear, right? So if I want to ask a question like, what's the likelihood of ending with less than 15, right? Well, it's essentially the area under the curve from 15 lower. Now, in this case, I'm using a function called p norm, right? So p will give me the probability or the area under the curve from the normal distribution here. So I'm passing in 15, and then I have to give my mean and standard deviation, which are just for my sample. And so the answer is like 93%. So I would expect 93% of my experiments to end with less than 15 heads, or 15 or fewer, that final number being 15. If I want greater than 15, well, because the area under this curve is 1, right, I could just do 1 minus. So the one thing you need to recognize is that the p function is always going to give you the area to the left of the value you get. That's just how R's functions work for these distributions. But because the area under is 1, I could do 1 minus. And we're gonna do this again next week. So, but do ask questions if this is not clear. So we interpret these as probabilities. It's a likelihood of being, greater than or less than 15. Okay. So what we're going to try to do, the next step that we're going to do over the coming weeks is say, well, we ended with what was the mean in our example here. Well, overall, but if we had a single sample and we had -8, so then the question is that far enough away from the center for us to be suspicious of the coin, right? That's the kinds of questions we're going to start to get to. And we're going to leverage this notion that, Well, we know that if we were to be able to repeat this experiment over and over again, in other words, collect the sample we have over and over, the distribution of those outcomes are going to follow the normal distribution. And with the normal distribution, we know when we go 1, 2, or 3 standard deviations, what the percentage of values in that, theoretical infinite number of samples we could do, we would observe. Okay, did that. There's a few other kind of really useful pieces here. And one is it allows us to then compare scores on different scales, because now we can kind of quote unquote standardize things. And we'll do this quite a lot. So one of the classic examples is there are 2 major admission tests that you may have taken to get into college for an undergraduate. You might have either taken the SAT or the ACT. And I'm old enough to remember when you took the SAT if you lived east of the Mississippi, and you took the ACT if you lived west of the Mississippi. However, I do believe the ACT has overtaken the SAT in popularity. But if you hang around Angela and I enough, and Dax project, I will frequently rail against the problems of ACT and SAT, and quite frankly think they should be eliminated. But that's a story for another day. But we're going to use it to try to teach stats because it's really useful. So SATs are designed, well, this may not even be current, so you guys can correct me if I'm wrong, I think this is when there were 3 assessments, but maybe not. But, they're designed to be normally distributed with a mean of 1,500 and a standard deviation of 300. And the ACTs are designed to have a mean of 21 and a standard deviation of 5. These may fluctuate a little bit from year to year, but that's generally what the psychometricians try to design these assessments. Okay, so if you're a college admissions officer and you got 2 applicants, you got one from Pam who earned an 1,800, but she took the SAT, and you got Jim who got a 24 but took an ACT. Who should you admit, right? Now, the key here, I should say up front, which is not a statistics calculation, if you will, you have to, it's more of a measurement thing. This presumes both the ACT and the SAT are measuring the same thing. If you're going to do these comparisons, you really should make sure they're comparing the same thing. So how do we do that? Well, we have this thing called a Z-score. And this is simply a linear scaling of the score. So if we take the observation and subtract the mean and then divide by the standard deviation, what we end up with is a score such that the mean is 0 and the standard deviation is 1. So all we've done is taken whatever the raw score or raw scale scores are and just transferred them or transformed them so that they now have a mean of 0 and a standard deviation of 1. Okay, so if we do that for both metrics, we now have them on a common metric scale. We'll call the Z-score. So we could do that. So we could take Pam, right? So Pam got an 1,800, so we're going to subtract 1,500 and then divide by 300, which is standard deviation for SATs, and we get a 1. What does that mean? So that means Pam scored 1 standard deviation above the mean, right? That's actually a pretty useful on its own way of comparing individuals in terms of standard deviation units away from the center. Okay, so if we take Jim, right, so he got a 24, but the mean of ACT is 21, the standard deviation is 5, which is 0.6, right? So Jim got a 0.6, okay, which is 0.6 standard deviations above the mean. Still good, but not as good as Pam, okay? And if you watch The Office, that's probably, hopefully the same conclusion you come to. Okay, so this was a slide I had in the data summarization slide deck that I kind of punted. So I want to talk about this right now. It's kind of a combination of a data visualization and a standard score problem. So I have this Shiny app. Oh, it quit on me. Why did it quit? Hold on one second. Which means my little thing. Okay. So here, this is a silly little data set, but it's kind of common if you're in the finance world. And these kinds of graphs are, I think, particularly common in the finance world, where here we're trying to compare the New Zealand US dollar exchange rate versus, product sales. I can't remember what TWI is. I think I had it on the slide. So TWI looks at the relationship between trade weighted index. Okay, I'm not a finance person. I'm not entirely sure what the trade weighted index is, but I assume it's some measure of the health of a trade between two countries. Okay, but the New Zealand exchange rate, right? That's just a ratio essentially between New Zealand dollars and US dollars. And then this is just something else, right? Not dollars, which is the point. They're two different metrics. Okay. And so a lot of times people want to plot these together. And one of the key reasons is they kind of want to look at trends over time. So there's actually really this third variable that they're kind of trying to look at. And this is often, how it's plotted. And you could look at this and say, is there a relationship between these two things? And one of the problems I have with these is that really what you want to look at is the relationship between the New Zealand, the exchange rate and the trade index, right? And so this is for each point here is a year, and we're looking at that. And we'll get into defining this, but you can clearly see these are highly correlated. But if you look at this particular plot, the kind of way I set it up, you might not detect that relationship, okay? In fact, the correlation is 0.88, which is quite large, right? So what I always suggest when you do this, right, and the reason why this is misleading is as a visualization creator, I can change the axes, right? So you can see the red on the left is the exchange rate, and on the right, I have the trade index. So the issue is if I pick any point on this plot, right, is this value 0.7 or is it like 145, right? It could mean two different things. And as I change the range on the y-axis, right, I'm actually changing what those values are. So, I used to be like with pie charts, like these are just really bad charts, but I understand why people want to use them. So my suggestion is the z-score. So if I go to this tab, if I convert both of these metrics to a standard score, then we're talking about deviations away from their respective means. But the z-scores kind of standardize it. So now they're on the same unit. And what I like about this is this actually takes the decision away from the plotter, right, or the visualization person, and says, well, no, these are equal. And so on this particular plot, I even labeled it. So here's the center, right? So this is the mean across all time. So for the exchange rate, the mean is 0.63, but for trade index, the mean is 65.77. So kind of force them together. And if you go back here, I could select, if I set this back to the default, right, this is using z-scores. But of course, what I want you to do is just play around, and you can manipulate these graphs to obfuscate the relationship that you're really trying to do. And that's all. I think the way you can get around the issue of these types of plots is through z-scores. Anybody here working in finance, do you see those kinds of dual scale plots often? Yeah, a little bit. There's another, I don't know if I should bring this up. There's another, if you're in New York City, the mayor is kind of getting some heat for another misleading graph where he truncated the y-axis with crime rates, trying to argue there is a huge increase in crime from one year to the next. And that's because he just truncated the y-axis to make the bars look really different. But if you back out and look at the 20-year trend, it's sort of not really a significant difference from last year to this year. But anyways, another case, another lesson to learn from misleading visualizations. All right, back to our standard normal distribution. So here in the top left of green, we have, this is essentially the standard normal distribution, right? We have a mean of 0 and a standard deviation of 1. This is also a normal distribution, but the mean is 19 and 4. So even though these are both normal distributions, not all normal distributions are equal because they're contingent, right? And that formula is like given a mean and standard deviation. So be careful, because I plot these. If this is using the default R plotting, they look the same and you might be misled. But when I plot them together, you can clearly see, in this case, the standard normal looks to be kind of, short and tall. And this blue one is kind of wide, right? And not as tall and shorter, right? But the key here is the area under the blue curve, the area under the green curve are both 1, right? So there's both normal distributions. All right, so interpreting, right? So if we know the mean and the standard deviation, and if we know that the distribution is normal, then we can say things like 68% of students are going to score between a 1200 and 1800, right? And then we can go to this last one, right? So 99.7% of students are going to score between a 600 and 2400. And when I was in high school, everyone says, don't worry about the SATs. You're going to get $500 or 500 points for just writing your name on the paper, right? And the reason being is that, getting less than a 600 on the SATs, you have less than a 0.03, actually a 0.015 chance of getting less than a 600 on the SAT, just by virtue of the design of the assessment. But of course you could pretend, if you don't answer anything, you will get a 0, but it's kind of an invalid assessment. Okay. The key, and what I just said, is assuming the distribution is normal. So in the lab for this week, and I think I saw a question come in, I think earlier today or yesterday, and I'm not sure I addressed it. If you're having issues with the QQ sim norm, ask it in a few minutes, because I'm going to show it and then we can look at it. So here, this is a simple little data set with 100 the height of 100 males in inches, right? Which we want to know, is this a normal distribution? Because we want to use that 68, 95, 99% rule. So the first thing we can do, right? Of course, first thing you always do is plot it. Histograms are great. They're easy, they're quick, and a quick evaluation. So here, we get this big drop here, which might be of concern. But of course, the problem with histograms is the width of your bins can really skew your interpretation, right? So sometimes you have to play with how many bins you have, depends on how much data you have, right? So one thing you could do is just superimpose a normal curve over top your histogram, right? That kind of gives you a reference point. So that's fine. You can do that. Here I could say, well, looks kind of normal. But really, one of the better tools is what's called a normal QQ plot, or quantile plot. So what we have here, and sometimes they're shifted. So the real values are, in this example, plotted on the y-axis. Okay. But then on the x-axis, what we're going to do is construct the probabilities from a normal distribution. So we're going to take each value and calculate its value as if it was a normal distribution. And then we have this line here, this blue line. And if all the points fall on that line, that means the observed values fall exactly on the normal distribution. Now, of course, that's unlikely. So what we want to just see is small variations. Now, one thing you note here, going back to our data type discussion, we kind of have this step effect here. And that's because the measurements are in whole inches. We don't have fractional inches. So all of these gaps is just because of a lack of fidelity in our measurements. If we had fractional inches, well, then it wouldn't look so much step. But this is actually, picked because this is really nice. Heights do follow a normal distribution. All the points fall really close to the line. So we'd probably confidently say that this data set follows the normal distribution. Now, things you might see are things where you have like it curves up, which is usually indication of a right skewed. If it bends down, you have left skewed. If you have kind of these S shapes, then that means you have longer tails than may be expected. but this is the function you're going to use in the labs, right? Which is QQ norm sim. And what this little function does is, in the top left panel is the same QQ plot I created here, right? I'm using the heights, right? So that's the raw one. These other 8 panels, and I'm sorry, it works better if you can blow it up, if you have a big monitor and kind of zoom in, but these other 8 ones actually are going to simulate a data from the standard normal distribution using the same mean and standard deviation and then plotting it. So these are all, randomly generated, but using the same mean and standard deviation from our raw data. And so what you're looking for, right? Look at this one right here. Look at, so this is theoretically should be the normal distribution because we sampled from that. And we kind of get this flare off, which is pretty common. Usually at the ends, you're going to have some points because you have fewer data in the tails. And so they kind of misbehave more. So when you're looking at this figure, I just want to say, is my QQ plot with the actual data, better than these other simulated ones? So it gives you just kind of a reference point to know, well, how much deviation from this line is acceptable, right? Like this one here even looks almost like a little less, but again, like the meat, right? From -1 to +1 standard deviations, where 68% of the observations are going to be, really kind of draws on that line. So it's really only an issue when we get out. So for this one, I would conclude, yeah, we're pretty good, right? This is a normal distribution. All right, we got about 19 minutes. I'm going to introduce one more distribution tonight. And I'm going to start with Milgram's experiment. I like this one because it introduces a common type of outcome that we're going to deal with. But I also like to just take a moment. This is my probably one attempt in the semester to talk a little bit about ethics in data science. I don't really get too many opportunities in this course. For those who don't know, Milgram, this was a study conducted after World War II. And one of the things Milgram was trying to do is understand how the Holocaust could have occurred, right? How did so many people just comply with orders to commit such heinous acts? And so he devised this experiment where there were three participants, right? There was an experimenter, a teacher, and a learner. Okay, the teacher was somebody who was recruited to be in the study, and I think they were largely undergraduate students. The experimenter and learner were actually in on the study, and the way this worked is the teacher was giving orders to the learner or trying to get the learner to learn something, and if the learner got the answer wrong, they were supposed to give them an electrical shock. And each time they got a question wrong, the severity of the electrical shock would increase to a point where it would be clearly lethal. Now, there was no electrical shock. The learner was never shocked. They were an actor. And so they kind of writhed in pain as it was supposed to increase. The experimenter, right, was there observing and would be telling the teacher, no, you need to give them the electrical shock because they got the answer wrong, right? So he kind of devised this experience to try to get to, like, in Germany, who they had people giving order and then people actually doing it, and how they go through. I'd like this because we'll talk about the outcomes in a second, but this and along with the Stanford prison experiment that were happening around the same time in the 60s really led to, I think, social science kind of having sort of an ethical awakening, if you will, right? I think IRB's Institutional Review Board. So thanks to Angela, who did a lot of work in getting us IRB approval for our current research project. It's kind of laborious, right? But it's necessary. And one of the reasons they exist now is because of Milgram and because of the Stanford experiment, right? We're like, because some people were harmed, right? Potentially mentally, harmed in participating in this, like, oh my God, I would have given somebody a lethal shock, right? And so now we have to consider, the harm to people who are participating in our research studies. Similarly, after, actually kind of around the same time, I think physics went through a similar awakening after the Manhattan Project, right? Oppenheimer, right up to his death, kind of regretted participating in the Manhattan Project. And now physicists and other hard scientists think hard about how their science might be used, right? I think we're seeing at least some of those debates occur, around genetic manipulation now and the like. Why do I say this? Because I think data scientists, us as sort of a nascent field, need to get ahead of this, because I kind of see these things replaying. And I think some of the things that Facebook has done, particularly around Cambridge Analytics, if you're not familiar with that, you should be, familiarize yourself with that. Google and their image classification, they put on online an image classification that identified gorillas as African Americans, right? Really just kind of horrific things. And part of the problem is we're so enamored with these predictive models that we don't often stop and consider how they could be used or what the harm of those uses might be, right? I think Facebook is facing a lot of backlash because, and YouTube should as well, is like when you optimize, if your outcome variable is attention and you optimize prediction models for attention, then recommending more and more extreme things should not be a surprise. But data scientists haven't been considering this. So do I think there should be a data science ethics board or IRB similar? I don't know. Honestly, I don't know. But I just raise this as like, think about this as you're going through your career. You're kind of new in the data science program. This will come up over and over again. Anyways, but from a statistics point of view, all right, there's two outcomes, right? Either the person gave a lethal shock or they didn't, right? So we have essentially a dichotomized outcome. And just for sakes, Milgram found that about 65% of people, obeyed the authority and gave the shock. And Milgram, this study's been replicated in different ways, and I think you get fairly similar results. So if you're a history person or you just want to understand that, Milgram may have provided a little bit of insight, but there are some criticisms to it because it was largely college students and the like. But okay, so when you have a dichotomized outcome, we essentially have what's called a Bernoulli sequence, right? So each person in Milgram's experiment can be thought of as a trial. And that trial is either labeled a success or a failure. So we have one of two outcomes, right? And so the mean in this case is the probability of success, right? So mean is going to be measured a little bit differently. But if you code this as 0 and 1, you can just use the mean function in R, and it's going to be the same as the proportion of success. So in this case, success is 0.35. And that's going to be what we're going to call our mean, or our measure of center, or probability of success. So so when it only has two outcomes, it's called a Bernoulli random variable. Okay, and this is how we write it out mathematically. So we have some other researcher come through and wants to repeat Milgram's experiment, but she wants to know, how many times do I need to do this before I find someone who will not inflict a severe shock? Okay, so it's a slightly different question, right? But the trials are the same. So the probability of the first person refusing is 0.35, right? That's what we learned. But what about the third person, right? So then we would have to say, on the first trial, we want failure. On the second trial, we want failure. And then on the third trial, we want success. So 0.65 times 0.65 times 0.35 is about 0.15. Okay, so about 15%. If you do 3 trials in a row, the likelihood of the third person refusing is about 15%. What about the 10th person? Right, so you can see where you can extend this question, and it's going to make the arithmetic a little bit harder. But this all follows something called this now creates something called a geometric distribution. So a geometric distribution describes the wait time until a successful, independent, and identically distributed Bernoulli random variables, right? So a couple of keys. Each trial has to be independent, right? Knowing the outcome of the first can't inform the outcome of the second, right? That's critically important. So if you're talking about, I think we mentioned a little bit about some of the card games, right? In poker, each hand is not technically independent because you're not you're not putting the cards back into the deck, right? They kind of go away. Although they get around that by using lots of decks. So the shift in independence is small. And actually, I'll show some simulations in a couple of weeks that shows about how far you can go, violate this independence assumption where it might not be a problem in your estimates. But for now, let's keep pure. Each one needs to be independent. So in other words, once word got out about Milgram's experiment around campus, right, would have been a problem for this. Okay, so we have geometric probability. So the probability presents the probability of success, and 1 minus p represents the probability of failure, and n represents the number of independent trials. So we're just going to write this out, right? If we look at this, what did we do? Failure times success. So all we've done is really generalize this. So we're taking the probability of failure to n minus 1 times the probability of success. So that's our geometric, that defines our geometric distribution. So how many people does Dr. Smith expect to test before finding one that refuses? So now we're getting, what's the center, if you will, of this geometric distribution, right? Or what's the expected value? So it's defined as 1 over p. So mean is 1 over p. So Dr. Smith would need to test 2.86 people. And now, of course, we don't have fractional people. So we would probably round up and say you need at least 3 people before you get one person to not administer the shock. Okay. So in terms of these kinds of geometric distributions, so here's our measure of the center or mean, and then we have a measure of spread. Okay, so the measure of spread or sigma here, the standard deviation, is essentially the probability of failure over the probability of success squared, and you take the square root of that whole thing. So this is the inside the quotient here is the variance, and of course we take the square root of it to get the standard deviation. So going back to Dr. Smith's experiment, so need to test 2.86 people, give or take 2.3, right? So if you go to, what was it, 2.86? So if I add 2.3, I would have 4 or 5.1, right? So if I get to 5.1, I'd have, I have to add 68 divided by 2, which is 30. What did I say? 68. So it should be 34, right? So I added 34% to it. Likely, right? There's still cases that I might have to go further, right? Because there are tails here. All right, let's break this down a little bit further. Now, suppose we want to randomly select 4 individuals to participate. What is the probability that exactly one of them refuses? So we're switching the problem a little bit. And so we have Alan, Brittany, Caroline, and Damien, or ABCD. And so one way we could do it is write out all the scenarios, right? So if Alan refuses, then the other 3 need to give the shock. If Brittany gives a shot, well, then the other 3, right? So we could write this out. And so the probability of only Alan refusing is 0.0961. And of course, it's going to be the same regardless of where it is. So then the probability of exactly 1 administering is simply the sum of those values, or about 38%. So if we had 4 individuals, all the combinations that could occur where 2 could have refused in some instances, 3, or even, probably rarely all 4 refused, but it's possible, right? You can imagine all of the scenarios, and 38% of them, exactly 1 of them refused, is what we're saying here, right? And this is kind of an interesting problem that comes up. And this will come up much later because this is the foundation for some of our prediction models. This defines what's called a binomial distribution. So we're looking for the number of successes. Here we're going to represent as K, and some number of trials represented as N, right? That's what we're interested in. And so the number of scenarios, so there's a little less tedious way, right? So in the case of 4, we can work that out. So we have the probability of success raised to the number of trials we want times the probability of failure times N minus K, right? So the binomial distribution describes the probability of having exactly K successes in N independent Bernoulli trials with probability of success P, right? A lot of our data science problems revolve around dichotomized outcomes. If you're in advertising, did the user click on the ad or not? Right. So success is clicking on the ad. For us, did a student pass their course? Right. They pass or they fail. So, or were they retained? Did they graduate? Right. So we have a lot of dichotomized outcomes, and we're trying to look at the number of successes we could get. Okay. We need to take a little sidestep, because in order to get all of the possible combinations, right, we need to do this choose function. Oh, and why this displays correctly in RStudio. The K should be underneath the N. I don't know why it's not displaying. What if I refresh? No, it's not. Okay. That's weird, because it looked fine when I was looking at it in RStudio earlier. Okay.
Like N sub K or N over K?
There's no slash. So we're choosing, we want to know how many successes we get in N we want K successes in N trials. So really all we're doing is trying to calculate all of the total number of possible combinations that we can have. So it's usually written as just N over K in parentheses as a choose function. In R, we're going to use, it's actually called choose is the function. But when you write it out, mathematical notation, the letters are just written on top of each other. And I don't know why it's not rendering correctly here. But regardless, let's look at the right-hand side. So to get this, right, so if we have, so in this past example, we had 4 trials and we were looking for 1 success. Or actually, I guess I'm going to do the example. I want 2 successes in 9 trials. So in the numerator, I have n factorial. So factorial, if you don't remember, is you take the integer. So in this case, we have 9. So n factorial, 9 factorial is equal to 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. So that's how the factorial works. So if I'm doing 9 over 2, so I have 9 factorial, which I'm going to write as 9 times 8 times 7 factorial. The reason why I'm going to do that is because in the denominator, I have 2 factorial times n minus 2 factorial, which is 7 factorial. So then I'm going to have 2 times 1 and 7 factorial. So these 2 bits cancel out. And then I have 72 over 2, or 36. So if I want exactly 2 successes in 9 trials, right, there are 36 ways that could occur. Now in R, there's a function called choose that will do this for you, right? So you're just generally going to use that. So why the heck do I need that? Because in the binomial distribution, we need to know, again, it's not displaying correctly here, so I'm sorry. So this is the choose function times that formula we had at 2 slides ago, right? So we need to know the total number of combinations that can occur. All right. And this is actually what it looks like, right? So in this example, so our probability of success is 0.35. We have 4 trials. And so here, this is actually the full binomial distribution for this example. So we were looking at 1, which we calculated, what was it, 38%? I already forgot. Yeah, 38%. Which is hopefully the height of this bar. But this is the full specification. So the height of getting no successes is what, maybe 18%. 2 successes is probably right around 30. 3 successes looks to be about 10%, and 4 successes, all 4 were successful, is somewhere really low, 2% maybe, right? A couple of things to note. If I sum the height of all these bars, I get 1, right? Again, now we can then interpret the heights as probabilities in the same way we interpret the area under the curve under the normal distribution as a probability. Now here, this is a discrete variable because binomial is discrete. So it's really just the height of each bar has to equal. So there, we can't have a 1.5, for example. We can't have 1.5 trials. We have 1 trial, or 1 success, or 2 successes. Okay. So here I'm using the D binom is going to get it in R. We'll go into more detail about this next week, again, about the class of these P, D, R, and I can't remember the 4th off the top of my head. So that's the binomial distribution. So just to summarize what we talked about tonight, right? So this is kind of foundational. We defined the normal distribution. which is going to be probably the most common distribution we're going to use when we have quantitative variables like height, GPA, dollars, right? Anything like that. Then the binomial distribution is going to be probably the most common distribution we're going to leverage or use in the case where we have dichotomized variables, true or false. And we're looking at, the ratio of success to failure. Okay. And that will get us through a lot of modeling as we go forward. And this is going to be sort of foundational to doing regression in a whole bunch of different ways. All right. Look at that, right on time. Let me copy this link into the chat and we'll be happy to answer questions.
Do you have a preference for using pnorm or like we did a homework in the bridge using norm.cdf and norm.ppf using Skype and NumPy?
I mean, you can use whatever you're comfortable with. I tend to prefer like the PD functions because they are because they're sort of a standard format. And if I can get to, I mean, I'm going to show this more formally next week, I think it is, but I think I have an R script here somewhere. Distributions, I think it is. Yes, this is it. So if I take this, let me sign into here. All right. Like I said, I think I'll talk about this again, but it's worth going over twice. So, so I have this function here. So here, so once I define that, I think, I've started to put this into a package, but I don't know if it's final. Oh boy, I didn't load cowplot. That's why. So if I do, so here I'm looking at norm, right? And so this is the plot I like. I actually use this all the time to try to remind myself of what the different ones are. So this is the normal. So in R, there's D, R, Q, and P as functions that are always followed by the name of the distribution. So we have, tonight we saw norm and we saw binom, but there's a lot. We're going to talk about chi-squared. We're going to talk about F. We're going to talk about T this semester. And those are the ones I can think of off the top of my head. So if I want to go to, to the F distribution, there's a DF, an RF, a PF, and a QF, right? So they all work in the same way. So once you kind of learn the pattern, I like this approach a lot. So for the D, right? So for a normal distribution, here's our normal distribution. And, so the D norm is really giving me the height. So the dot is the input to the function. So D is giving me the height of the function of the distribution at some input value. So R you don't have any inputs parameters. It just gives you random values from that distribution. So that R is for random. So D is for density. Okay. So P is for probability. Now, the relationship between this and this is the cumulative distribution function, meaning what we're doing is I'm just taking, as we go from left to right, I'm just sort of summing essentially that D as we go through. So you could see over on the left, I have 0. By the time I get all the way to the right, I'm at 1, right? So another way to think about that is that it's giving you the area under the curve to the left of that point, right? And that's essentially what P norm is going to give me. So if I have 0, right, I'm at 0.5. If I go to this value, which I don't know what it is, it's actually I can tell you it's 0.5, right? Then I get an output of roughly 0.7. So in other words, if this value here, the area under the curve over here it would be roughly 0.7 or 70%, right? And then Q norm is if you have the height of the function, I'm sorry, if you have the probability and you want to know where on the z-score essentially it falls. So these are how these kind of 4 class of functions work. And like, oh, go ahead.
I wasn't going to ask, but are z-scores always normalized? So if you have a z-score of 0, that's always 0.5. If you have a z-score of 1, it's always like a cumulative distribution function of like a z-score of 1 is always going to be 0.68.
It's actually not. It's going to be 0.68% is 1 standard deviation across the mean. So what you would need to do is, so if I was going 1 standard deviation here, so I would have 68% is from here to here. So I would actually take half of 68, which is 34. So up to 0 is 50%. And then I would need to add 34%. So 84%.
Yeah.
And that's how percentile ranks work, right? So in other percentile ranks, if you got those on your SAT or ACTs, it's what percentage of students scored lower than you. And that is kind of drawn from the cumulative distribution function. I have another one that we'll show next week that actually shows the P norm with the normal with the shaded area. So we'll look at that soon. But the reason why I like that is, so that's P norm. Let's look at the F distribution, right? So this is just different distribution, but so the shapes are different, and we'll explain why the shapes are different when we get to ANOVA, which is where this shows up. But the area under this curve is 1, but in terms of the class, right? So we still have D, we still have R, we have Q, and we have P, and they are behaving, right, in terms of inputs and outputs, they behave in the same way. Right. So you could see here in this little script, here's the T distribution, this chi-squared work. Yep. Chi-squared works. This plot distributions, I was trying to make it generic, but it kind of breaks down when you get to discrete distributions like the binomial. And I haven't solved it yet. I mean, I could do binomial by itself, but it's, and those functions still exist, but in a lot of ways, like I know we're technically you're supposed to have calculus to get into the program, but I try to presume very little calculus knowledge. I mean, these are all just integrals and then we're going to see it in a little, much later, derivatives. But in terms of how we evaluate these distributions, we're really just taking integrals. And so taking the integral from the binomial is tricky. It doesn't work using the integrate function in R because it's not continuous. Just as an aside, and if what I said in the last 15 seconds doesn't make sense to you, that's okay. You're not going to be tested on something like that. Other questions?
So there were 2 bits in this week's lab that didn't go the way I expected it to. I did ask a question in Slack and it seems like someone answered that. But I haven't had time to try out and see if that works.
Did you ask about the plot function not working?
Yeah.
Yeah, and if you encounter it again, it would be great if we could maybe jump on a Zoom so I could see it, because I actually got your error message, but then when I cleared my session, it works. So I suspect there may be a naming collision.
I'm sorry, you froze on the important parts of that sentence. Can you say it again?
Back. Yeah. If you get the error message again, and if we can get on a Zoom call, I suspect that there might be a naming collision, meaning there's a function name that exists in 2 different packages and it's calling the wrong one, like, okay. Which is why when I went to session restart R and then just reran the document interactively, it worked. So I think I loaded a package that might have a function of the same name, and it's in R, the last one wins. So if you load another package, in fact, sometimes when you load a package, you might see a warning message that says,
Mhm.
function X is masked from something, and it's telling you, oh, this package has a function that is already available. It's now going to behave differently. And this was in the early days of ggplot, a real problem, because I'm a big fan of the psych package. I use it all the time. And they have a function in there called alpha, which calculates Chromebox alpha, right? It's a reliability statistic. ggplot had a function called alpha that had to do with the transparency of objects on the plotting frame. Very different
Mhm.
things, right? And it would just,
Yeah.
and anyways.
No, that makes sense, given the answer that somebody else suggested in Slack, which was basically to put in the library that it was coming from.
Yeah.
What you said makes sense, and that response will work because it'll say, take it from here. Can I ask my other question?
Please.
Without, I don't want to take everybody's time, but for exercise 3, where we're making the normal probability plot of the simulated normal that
Mhm.
we did, and you said since sim norm is not a data frame, it can just be put directly into the sample argument, and the data argument can be dropped.
Is that what I said? I vaguely remember this. Let
Yeah.
me go look. I'm going to Slack
That's
right
what
now.
you said, and that was not my experience. ggplot seems to always want a data frame, and so
Oh, really?
obviously I'm new to R. Maybe I'm misunderstanding something,
Let
but
me see. Let me see. Trying to.
yeah.
Why can't I find the message? Which channel was it? A private message or?
Nope, I didn't message about this one.
Oh, okay. I was trying to look for it. So,
Nope, sorry, didn't message about this one.
Okay. Let's.
I'm asking it now. I can message about it.
No.
again if that's an easier
So
thing.
let's. Well, you can always do. So if I do, let's just do. Just because I'm not feeling creative at this hour, I'm going to load the classic empty cars. And
Mhm.
so I want to do a geom histogram. I thought I could do empty cars. Is that? I probably have to load. Oh. Yeah, you might be.
Yeah.
So what if I do data
right.
equals empty cars? And then I say AES X equals MPG. So, yeah, I guess you need, so I just happened to specify it in the geom where you could, could do it this way. That should also work.
Right, but we don't have a data frame because sim norm isn't.
Okay,
a
so
data
this
frame?
this is in lab 3.
This is in lab 4,
Okay, let's take a look.
and it's exercise 3 within lab 4.
All right, first thing I want to do is I'm going to clear my R. Exercise 3.
Right, so right there
So let me run
is
that.
where you create sim norm.
Mhm.
And then further down, you're saying make the normal probability of sim norm, just like in your example, you did it for the Dairy Queen data.
Okay, so let's look at the Dairy Queen. Oh, okay. Yeah, I'm sorry. So let's make a note of this, Angela. I can fix this up. Let's talk about this tomorrow. So here's what I would suggest. I don't know where this is going to belong. So you can always create a data frame kind of inline like this. And then I could just say X equals X. So I think that will work. Yeah. So let me cut and paste this into the chat for you. So because SimNorm is a vector, right? Here's a, if you
Mhm.
haven't come across this, I like class. So it's a numeric vector, in fact, right? So it's one dimensional. So you can always kind of create this data frame inline like this. In fact, when I do that, I might not even need the AES if no, I do. Okay, never mind. Used to be, it would presume, it would look for X if you didn't specify X, but I guess it doesn't do that anymore.
Yeah, I tried different ways of forcing a data frame, but I didn't try the one that worked.
Yeah, I'm sorry. We could either use this as the example, or I mean the other way to do it that could be cleaner is you could do it here, right? We could say X equals like so. So now if I look at SimNorm, right, it's a data frame with one column. So now I would just do this, right? Because SimNorm is now a data frame. Yeah, that's an unnecessary tricky part. We can fix that. Clarify that.
Thank you.
Yeah.
I'm glad you said it was unnecessarily tricky because I thought I was just missing something entirely.
Yeah, no. Nope. Glad you asked it. Thanks. Other questions? Going once.
Shiny project. Can we build our final project using a Shiny app, or can we embed
Sure.
a Shiny app in a final project?
Sure. Yeah. Yeah. We are, go ahead, Angela.
Just make sure that your Shiny app works before the final presentation.
Oh, yeah, we had a
because-
student last semester. Yeah. Yeah. Make sure it's running. So
Yes.
start it up. So look at like tonight before I got on, I was on sitting in my chair around 7 o'clock, starting up this Shiny app that I knew I was going to show tonight, and played around with it, and it was working, and I was ready to start sharing. Of course, I did it too early because it timed out. So, but but yeah, that's what I would recommend. Just make sure it works.
Yeah, that'd be awesome.
But we and yeah, we could well, Angela and I need to, we're presenting in April a poster, and it's a digital poster, so we're going to build a poster in Shiny, so people can interact with the data a little bit. I think so we could share our experience once we have that.
That's cool.
Other questions? All right, well then I'll hang around for a few more minutes. I'll stop the recording, but just again, reminder, 3 o'clock next week. If you can make it, that would be fantastic. If not, the recording will be up by 8. I hope, unless something goes wrong on my computer. Otherwise, have a great week, and we'll see you soon.
I have a quick
Thank
non-recorded
you.
question.
Yeah, sure. Yep.
With